Okay, so that was using Hess's law. We can actually also calculate the standard heat of reactions. This little degree symbol means standard, and that has to do with standard states for particles. I'll tell you more about that in a minute. Okay, so this is going to look really, really scary. It's actually not. It is the summation. That means we're going to add things up of delta H0 of your products minus, you add them all up, of all your delta H's of your reactants. So what you have to remember here, this is not that scary. Okay, always remember it's products minus reactants. The rest is just algebra. It's plug and chug. It's not hard. It looks scary. So here, N is going to equal your coefficient, your number of moles from your balanced equation. So moles of whatever. So you're going to use your equation. So you start with the products. Remember, products are going to be on the right. So you kind of work backwards a little bit. And if it says like 2 moles, you multiply it by 2. Now, elements that are in their standard states, that means heat of formation is 0. These are kind of assigned. We'll talk a lot more about this in thermodynamics next time. I guess I can use my pen again. Okay, so here we go. Heat and enthalpy are temperature dependent. So what we measure them at what we call standard state conditions. This is a little bit different than STP, okay? At STP, our standard temperature was 0. At standard state for thermo, we're assuming room temperature, so 25 degrees Celsius. If we have a pressure, we assume it's 1 atmosphere. If we have a solution, we assume it's 1 molar. So those are standard conditions. It's different. The temperature is different than STP, so just be careful there. That's not going to make much difference this semester, but know what it is. Okay, so what does this actually mean? A standard enthalpy of formation, so the degree symbol means standard state, the little f means formation, represents the enthalpy change when 1 mole of a compound is formed from its constituent elements in their own standard states. So here it would be delta H of your products minus summation delta H of the elements. Now, fortunately, the book does this for you. Okay, elements that are in their standard states, we've already said this, is 0. Now, there's a short table in the book, and it's on page 276. So let me get this out real quick. 276. Of course, it's on the wrong side. Okay, so there is a table here. That's what it looks like. And you have to pay attention here because the units here are kilojoules per mole, but it gives you everything. This is a brief table. So note the elements as they occur in nature. It doesn't take any energy to form them. So like hydrogen gas, it doesn't take any energy, so it's 0. Oxygen gas is 0. Just solid sodium in its standard state is 0. That makes calculations easier. Now there's another big one in the appendix back here that's much more extensive. I think it's appendix, there it is, it's appendix 2, useful data. This actually gives you multiple things, so always make sure you're looking at the right substance with the right phase, because you can see here that like N2O4 occurs as a liquid and as a gas. Make sure you're looking at the right one. And also on here, make sure you're always looking at delta H. So we'll deal with G's and S's next semester. But so make sure when you're looking at this and you write down the correct units, because that matters. But you'll always have access to some sort of information. Don't bother memorizing any standard states. Okay, so there are several solid forms of carbon, you know, on the table there. But the one that has 0, that's going to be graphite. Like oxygen, standard state is the O2. That would be the diatomic, not O3, not O1. So if it says which one is in their standard state, pick the one that's 0. Okay, so let's give this a try. What is a standard enthalpy change for the combustion of methane? So here is our equation for our combustion of methane. This is really confusing and I don't like it. But what it means is what we're technically doing is we're breaking all of our reactants apart, and then we're reforming products. So we get energy, no, we use energy when we have to form bonds, and we release energy, no it's not, we release energy when we form bonds, we gain energy, it requires energy to break the bonds. Okay, so let's give this a try. Let's give this a try. So, if we look here, so yeah, cost and cost. Let's balance this reaction here. So methane 1 1 2 2 2 2. There we go. All right. So now let's see here. What we can do is we need to do summation in of our products. Always write products minus reactants. Okay, so times products minus in R. R stands for reactants. Okay, so start with the products. So I do these in brackets. I start with brackets and then I use parentheses. Okay, so here we have 1 mole of CO2 gas, and now we need to find what its standard formation is. Which, if you look here on this table, CO2 negative 393.5. Negative 393.5 kilojoules per mole. So that means the moles are going to go away. And then here we need to add up because we also have 2 of water. So 2 moles. And let's see, hopefully water's on this one. And it's gas water. So make sure you pick the right one, because look, see, there's gas and liquid. Find the one that's the gas, and they're different numbers, so be careful. Negative 241.8. Negative 241.8 kilojoules per mole. So we're done with the products. Now let's do our reactants. And we have 1 mole of methane. It's not on this table, but we can figure it out. So it is negative 74.6 kilojoules per mole. Sorry, I had to look that up. And we need to add oxygen, so there's 2 moles. Oxygen is a free element. It is in its standard state. So here, oxygen gas is 0. So that makes things easy. But I always include that just so I don't have to worry about it. Okay, so now I work inside the parentheses and the brackets first. Okay, so here, negative 393.5 plus 2, so you see adding 2 times negative 241.8. And some of you might want to do this in several steps, but I get negative 877.1, and that's just kilojoules because the moles cancel out. Okay, so those are my products. Minus, keep your bracket open, 74.6 kilojoules, because then that's 0. So sometimes I'll write down all the multiplication. As you get better at it, you might not need to do that. All right, so we have negative 877.1 minus, now put your negative 74.6. So our delta H of the reaction at standard conditions, negative 802.5 kilojoules. And that's the answer. This is not really hard. There's a lot of opportunities to make mistakes, meaning like you have to copy data directly from tables correctly, but it's not that hard.